shared one material to you, so please watch that. That would be useful for conducting your assignment. Actually, there I explained some of the method to use for use the Colab, Google Colab. Okay, so that would be useful. Okay, and today we will start to learn about the PyTorch library. Okay, and before that, actually there's one notice. This is 2 weeks later. Actually, 10 days later, we will have quiz 1. Okay. And that will cover some basics about deep learning and also PyTorch. So please prepare for that. So their coverage would be lectures 1 to lecture 1 through lecture 3. Okay. So spanning, till this lecture, yeah, the quiz range would be included. Okay. So last time we learned about differentiability, and roughly we can think if layers are differentiable, then we can train them. Okay, we can learn their parameters. Okay, and for specific layer whose parameter is sector, to make those layers differentiable, we have to define these 3 rules. Okay, the forward rule, which means how to process the input to generate the output y. Okay, this might be some of the mathematical formula. Okay, then this would be, this should be this differentiable, and it means we have to calculate this kind of 2 gradient from this forward rule. And actually, the backward rule means the differentiation of the output y respect to the input x. Okay, given this forward rule, we have to to train the layers. These 2 are actually the first one. The first rule have to be defined. And the next thing is the differentiation of the output y respect to their parameter sector. Okay, but in the exceptional case where a certain layer, if it does not have any parameter sector, then we don't have to actually define this parameter update rule. So for some layers which do not have any parameter within it, then we don't have to define this parameter update rule. But anyway, but for remained layers which have parameters, then we have to define these 2 gradients. Okay. And the reason why we have to define these 2 gradients is actually the parameters of the entire deep architecture, their parameter sector are learned using this kind of formula, which is called as the gradient descent. Okay, so this is the initial parameters which would be randomly initialized, and from that, actually this is via the chain rule. The thing we actually calculate is this DL, this sector, and this is actually the direction of the parameters that can maximize the loss L. Okay, so because it is the direction of maximizing the loss, we multiply the minus sign here, and also multiplying some of the scalar value, which is very small, and actually update the parameter towards that direction. Okay, that would become the new parameter sector. Okay, and actually this happens for each sample. Each training sample. In your training data, you have to have both input and the output y. So at this architecture, the initial input would be I. So I will, rewrite the symbols. We have to define multiple this kind of pairs of data, which would be called as the training data. So input image I and their corresponding label Y. We have to secure this training data as many as possible. And then for each training sample, we input them and calculate their prediction from the deep architecture and compare with ground truth and calculate the loss L, and then calculate the gradient, these two gradients for every layers in the middle, and actually calculate this DLD sector for every parameter and update the parameters once, okay? So this happens for each training samples, okay? So during the training, the thing we do actually is traversing all the training data one by one, and for each training data, we actually update parameter sector, okay, using their DLD sector, okay? Are you guys following this? Okay. So, when first given, these deep architectures are, like the baby who do not know anything, okay? So the parameters are random, but by giving him some samples, some instruction, the baby become to know about the data, okay? So given input, he become to know how to predict output, okay? So that is actually similar to what humans learning, okay? And actually today, from today, I will teach you about this PyTorch library, okay? Because, the deep architectures, it has many parameters within it, okay? So, for example, this layer would be implemented as the convolutional layer. We actually learned about this in previous lecture, or some of the pooling layer or activation layers, maybe, okay? In convolutional layer, it has many parameters within it, because, given C channels in input image, and if we want to generate D-channeled output, there should be this amount of filter corner, and if filter corner, their size is, let's say, n by n. N would be usually small, but normally 3 by 3 to 11 by 11. The filter corner for the convolution, that size would be like this. But anyways, we need to define, maybe for example, if the filter corner size is 3 by 3, but input channel is 3 and output channel is, for example, 64, then already there are a lot of parameters. So this number of parameters we have to learn during the training stage. This is for one convolutional layer, but we normally have more than 8 convolutional layers. So yeah, even it becomes very large. So in CNNs, which is the deep learning architecture, there are a lot of parameters. And it is sometimes very hard for us to manage all the parameters. In the code level, we have to type this kind of code for all the parameters. So it takes a lot of, a lot of lines in when you do coding by yourself. So this PyTorch provides you very easy interface to implement this kind of deep architecture. At the same time, when you try to implement these deep architectures using Python or C++, actually, you have to define these 3 rules in your code. Okay, without using this kind of library, you have to type you have to implement all the rules by yourself. Okay, but this kind of library makes it easy. Okay, And moreover, I mean, when you try to implement this kind of differentiable formula, then sometimes it may be difficult, okay? So for example, if your forward rule is some polynomials like this, you have to, define, in your forward rule, you do input x, okay? And you may implement this as return x multiplied by x, right? So you may have to define the forward rule like this, okay? And also you have to define your own backward rule. And sometimes you have to calculate the differentiation of differentiation of y respect to x by yourself. This is high school math, right? So if you differentiate this respect to x, then that would be this. And you actually implement this by yourself, okay? And also you have to define this parameter update rule given the input by yourself, okay? But the thing is, these two functions, these two methods are depend on the forward rule. If your forward rule changes, the differentiation formula is also changed. So you always have to re-implement all the backward and parameter update rule as well as this forward rule, okay? And sometimes this kind of formula becomes very complex, and even you cannot find the closed form solution for the differentiation, okay? I mean, in that case, this PyTorch library is making this kind of situation easy. What they do is they actually already implement the approximation solver for the gradient, calculating the gradient. Okay, so you may learn about some of the method that can approximate the this kind of differentiation. Okay, so that kind of algorithm is like iterative algorithm that can actually find the closed different gradient for given functions. Okay, so inside the PyTorch, they already implement that kind of iterative algorithm that can calculate the gradient. Okay, given this kind of forward function, they can apply those kind of approximation algorithm that can calculate this dy dx and dy d theta. One of the merit of having such iterative algorithm for approximating gradient is their algorithm will not be changed depending on the forward function. Okay, are you guys following this? Okay. So you don't have to re-implement this backward rule and parameter update rule. Given different forward function. Okay, so you can only implement one algorithm that can approximate calculating the gradient and can reuse that for any forward function. So PyTorch, it already implement that inside the library. So the thing we have to define is only the forward rule. Okay, we can only define this forward rule, and the rest of backward and parameter update rule, that kind of approximation algorithm can automatically, applied and calculate. Okay, and actually the way applying that kind of approximation, gradient approximation algorithm is just calling these two types of this function. Okay, so if you just call this low start backward function, then this kind of two gradient for each layers are automatically calculated, and So, I mean, you can automatically calculate DL dissector for each layer's parameters. Okay, I mean the order is like this. When you calculate, when you call this function, for all the layers, their backward rule and parameter update rules are automatically calculated, and then they are multiplied together, and via the chain rule for each layer, this DL dissector is actually calculated. Okay, and then after calculating this DL dissector for every layer's parameter sector, the thing you have to do is multiplying some small scalar value to DL dissector and actually add to previous parameters. Okay, and that this step is actually happen in the PyTorch by calling this optimizer.step function. Okay, so the thing you have to implement is just the forward rule. Then rest of thing, the PyTorch is automatically managing. Okay, so by calling this low step backward, it can automatically calculate this gradient. And when calling this optimizer.step, you can actually update the parameters. Okay, are you guys following this? This is very important actually. And subsequently, I will explain you how to implement algorithms in the PyTorch. Okay, so I would start from very simple algorithm, which is called as the linear regression algorithm. Okay, so this X is the input, and this Y is indicating output. Okay, and now X is also the scalar value, having just one floating value, and Y is also the scalar, which have just, one-dimensional, one-dimensional value. Okay, and linear regression is a regression algorithm. I'm assuming that all of you are already familiar with the difference between regression and classification. In regression, what we do is, given input X, we are wanting to map it to some continuous value. Okay, for example, this X could be, exemplified as the weight, and this Y could be exemplified as height of a person. Okay, weight and height, those are having some of the linear relationship. Okay, so when known some people's weight, we can estimate his height. Okay, so there are some of the linear relationship between X and Y in this situation. So in the regression task, our aim is, when we know their weight, we somehow wanting to estimate their height. Okay, that's the linear regression algorithm. In general, if we estimate some of the continuous value from some of the continuous variable, then it is called as regression. But linear regression can be applied when there seems like there are a linear relationship between X and Y. Okay, so in that sense, linear regression is kind of the simplest form of the regression. Okay, and also because it is linear, the X and Y is mapped with this kind of formula. So that's why it is called as linear regression. Okay, I already tell you that linear regression can be applied in the situation where X and Y seems like having the linear relationship. It means their formula have to be defined in the form of this. Okay, this is the linear equation in English. Okay, so linear means in Korean is 1차 함수. 1차 함수 다들 배우셨죠? 네. 고등학교에서 1차 함수 배운 거랑 같은 의미입니다. So linear means that, okay? And nonlinear equation, it means x squared or x. If the power of x is larger than 2, then it is called as the nonlinear equation. Okay. Anyways, linear regression, it assumes that the relationship between x and y, they are lying on the linear straight line. Okay. So this is actually some of the equation having this form, right? We have to define this A and B, okay, that can properly, relate X and Y. So, and also this blue point is meaning some of the samples. This is kind of the training samples given to you, okay, during deciding this A and B. In some sense, you can think this A and B as the sector we have to train, okay. Given multiple data, here we have 10 data samples, 10 X and Y samples, right? We have to define the sector, which is composed of A and B. That's the linear regression task, okay? And kind of, it can be formulated as standard machine learning problem. Okay. And now I will explain how we can solve this linear regression, which means given some data, how we can decide this parameter sector. There are multiple ways actually, but one of the way which is related to our context is solving this using the gradient. Okay, so we will solve this by initializing this sector, which is A and B, which is the parameter for this linear equation. We will randomly initialize them. So we will first randomly initialize these A and B values. Then that line would be like this, some random. It would be located in random space, and it at all decide, this X and Y, their relationship, okay? But we will gradually improve it by using this gradient update, okay? So using this, I will show you how we can update the parameter sector, which is actually the A and B. So sector are randomly initialized at the initial stage, but the thing we have to calculate then next is DLD sector, okay? So this is the direction, to minimize the loss, okay? Then we first define this loss, okay? This loss, we have to define that as the function of sector. Then we can calculate this DLD sector, okay? And this loss is the, I already told you that this loss L is the distance between ground truth and our prediction, okay? So this AX plus B with random A and random B, that will predict something, but that would be far from the ground truth Y. But anyways, we can calculate the loss, okay? So here, what is illustrated is, sorry. Here, the figures are having this kind of line, and that is actually meaning this loss, okay? The distance, because we assume that the initial data was having the linear relationship between input X and output Y, we can somehow, assuming that the data should be lie on this regression line. And this line is AX plus B, okay? Actually, when inputting this X value, our output is generated in this Y, okay? For given X, this Y value would be our prediction, okay? But during the training stage, indeed the data is located here. So this would be the ground truth, Y, okay? And this is our prediction. Are you guys following this? Right? And the distance between this prediction and ground truth, their distance becomes the loss L, right? Okay. Anyways, we can calculate this loss L for entire 10 training samples, okay? We can sum them for 10 data given here, denoted as blue point. And we can calculate this kind of distance by, this is ground truth. So, this is ice sample. So this would be our loss function, right? Are you agree with this? Right? So this is our prediction. When given x, ice x, we can calculate our prediction by multiplying a and adding b, which are the parameters. And by finding their Euclidean distance to their ground truth value ygt, then we can calculate their distance. And if we sum it for all the training data, then this would be the loss function, right? Okay, and then what you already know that, find that this is the function of A and B, right? Which is actually the function of parameter sector, okay? And then we can differentiate it respect to parameter sector to calculate this DLD sector. And using that, we can continuously update our parameter sector, which is actually A and B. Okay, are you guys following this? Okay. Is there any difficulty to understanding this? 다 이해되나요? Okay. And this is actually the code for implementing that. Okay. So this is the code for actually generating some of the data. So we will actually generate 100 data from the known, linear equation. So we first have to define this kind of true W and true B. So, and also here, our linear equation is, assuming that the X is sum of the vector, not a scalar. So that's why we have multi-dimension for this parameter A. So here we are assuming that our input is also having multi-dimension. So, output Y is scalar, but we are assuming that our input is three-dimensional scalar. So that's why we are having a three-dimensional vector for parameter A. This is actually A. And this is parameter B. This is the ground truth parameter A and ground truth parameter B, which will be used for generating some data. Okay, so using the ground truth W, I mentioned that this is A, but in this code, we use this as the W, Wx plus B. Anyways, using this W, we multiply it with the input and add the B true. Then this X and Y, and X is randomly initialized for 100 samples. Okay, so by executing this two line of code, we can randomly generate 100 training samples. Okay, are you guys following this? And also we have to randomly initialize our parameter W and parameter B with these two line of code. Okay, so these codes are for generating the training data, but we also have to initialize our parameter, which are W and B. Okay, so this means W is in 3 dimensions, and this is meaning that B is in 1 dimension. Okay. And gamma is meaning that some small scalar value in this formula, okay? Gamma is actually this epsilon, okay? It have the small value, and this loss is, the space for containing each step's loss, okay, loss L. And we have to iterate multiple times, and they set the total iteration number as 100. And the thing we have to do is, for getting this true B and true B, true W and true B, we first randomly initialize via this line of code, W and B. Then we will actually use this to update W and B to fit to the data, training data, okay? And that is actually happening here. So you have to calculate, okay, W and B, their gradient values should be first initialized as some known value, unless there would be some garbage value. So I will explain that again later. But anyways, we have to initialize the gradient value of W and B with known, unless there will be some garbage value. It's similar to initializing some of the variable in C++ with the 0. Okay, so you can think of this as just initializing the gradient value. Okay, and the first thing we have to do is, defining this kind of forward rule. Okay, and given this x we made, we multiply W on that and add the bias B. And this Y on the pred variable is the prediction from our network, okay? And then this Y is the ground truth value for that sample. And this is our prediction. And actually you can feel like that this is calculating the loss Euclidean distance between prediction and ground truth, which means the loss actually. This is calculating loss, and we, save it in loss variable. And the thing actually happen here is, you have to calculate without the PyTorch library. You have to calculate this. The dWdL and dLdB, which is the differentiation of the loss respect to the parameters you have. You have to calculate this. You have to implement your own code for calculating these two gradients. Okay, to use this DL dissector. Because your parameter is composed of W and B, your DL dissector is actually these two gradients. And you have to, by yourself, implement this part, how to calculate this given loss function. But because you are using PyTorch library, you can just call this loss stop backward function, okay? Then inside the PyTorch, actually, this kind of, this kind of graphs are defined, okay? Here, W is multiplied, and maybe W is multiplied with X, and B is added and predict Y. So by seeing this forward rule is composed of, this kind of formula. Input X is multiplied with W, okay? And then added with B, okay? By seeing this forward rule inside the PyTorch, they kind of generate this kind of graph structure. And then also this prediction is, they already know that this prediction is also calculated with the ground truth y. Okay, we already specified that here. So inside the PyTorch, by writing this kind of forward rule, this kind of graph structure is built inside the PyTorch. And if you call this low start backward, what is happen is actually you can, apply some automatic gradient calculation algorithm and calculate dy b and dy some of the, let's say this is the intermediate layer whose name is y1. Then this kind of gradient is calculated operational in the middle layers, and then they are combined to automatically calculate this kind of DLD sector, which we are required for learning this part. Okay. Because in the PyTorch, they are building this kind of structure, the graph structure, that have all the parameters inside and all the intermediate output inside. When calling this low start backward, they already know where to calculate this kind of gradient. And after calculating individual layers, this backward rule and parameter update rule, they can automatically also calculate DLD sector for all the layers automatically. Okay, that is actually happening when you call this low start backward. And then this is similar to this formula, right? Because you already calculate your gradient, which is DLD sector. So DLD sector is already set for each parameter sector values after calling this low start backward function. Okay, so here it is DLDW is stored already, and B.grad DLDB is already stored. And the thing you have to do is multiplying some small scalar value you set to these gradient values, and indeed add to previous parameter values. Okay, then this becomes the new parameters. Okay, and then this W and B become close to their true values after many iterations. Okay, and this is for visualizing the loss function. Okay. So after 100 iterations, so we iterated for 100 iterations. This is the randomly initialized value, and this is the true W and true B we used for generating the data. Then you can now find that their obtained value is actually same as the setted value. Okay, and this is the visualization of the loss L. For each iteration. So iteration goes to 100, and loss L initially, the distance between prediction and the ground truth, that is very high at the initial iteration, but it is gradually becoming less. Okay. Okay, are you guys following this? So actually, when solving this linear regression problem, there are multiple ways to solve this linear regressor. But now, this gradient descent is a very useful tool to solve this linear regression. And actually, you can use PyTorch library to easily implement that training code. So this is very short code for solving the linear regression problem. Okay, and as I told you, these kind of graphs are constructed when you just type this kind of forward rule. Okay, So B, X, W, those are PyTorch variables, okay? So this X is also initialized as the torch variable. And this operator are actually connecting the variables to make the final output. And also this is also used to calculate the loss, okay? And then, using this graph, as I teach you in previous lecture, if you are given this kind of graph via the chain rule, you can step by step calculate the gradient for all the variables inside this graph. Okay, that is actually automatically happened when you call this loop step backward. Okay, and after getting all the gradient values, then you can just simply run this update rule to update the parameters. Okay, and another important thing you have to note here is when you are initializing some of the variable with PyTorch typed variable, there are actually two instance value. I mean, b.data, it have the actual value for this variable b. Okay, if you want to access its value, then you can access b.data. But b.grad, it has the gradient value, actually DLDB. It actually have DLDB here. And b.data, it have indeed the value of b. Okay. So b.grad is also the PyTorch variable, so you can access b.grad.data to access this value. Okay. And for other variables, that's the same. Okay. So in the forward rule, you can think some of the variable data instances are calculated by applying this kind of operator. So y.data, that is calculated from this b.data, x.data, w.data. Okay, that's the forward rule. But in the backward rule, these gradient values are filled, okay, by calculating the gradient values. Okay. And the calculation of gradient that is happen automatically via the approximation algorithm. Okay. Are you guys following this? 질문 있나요? Any questions? Till now? No? Okay. And there are still few, things which might be, not trivial to implement if the parameters are, because the deep architecture, there are many parameters, right? So if, that was the simple case where training the simplest linear regression algorithm. So there was only two parameters, W and B, okay? But let's say in CNN, in convolutional layer, there are, as I told you, n by n, the filter size, and d by c, the multiplied by output dimension and input dimensional filter corners. And this should be more than layers. This kind of filter corners have to be there for each layer. So there are a lot of parameters, but even initializing this amount of parameters, you may require hundreds of lines of code. Okay. So to reduce that, you can actually define some of the layer function, okay, like this. So the title of this slide is PyTorch style code. Okay, you can initialize all the variables by yourself and add them together when defining the forward rule. Okay, that's one way to defining the forward rule, but you can also involve some of the predefined layer. In this type. So torch.nn.linear, that is actually the function having this form of the function. Okay, so this is a linear. So this is actually defining some of the linear layers. Okay, and this X could be multi-dimension, and B could be also in multi-dimension. Okay, and Y could be also multi-dimension. So here we can define it like this: input feature dimension is 3, and output feature dimension is 1. And bias means we can set this as 0, but if you set this as true, then you will have parameter B as well. So by defining this like this, your dimension of this W or A variable, the dimension of this A variable is also decided. So I mean here 3 by 1 array is defined, and they are actually randomly initialized. And B is also considering only the dimensions. They are randomly initialized. Okay, so by explicitly defining the architecture as the linear layer, you can define it using just one line of code. Okay, and also in PyTorch, there's also convolutional 2D layers defined already, and their hyperparameters is number of input channel, number of output channel, and stride, and the window filter corner size, and so on. So by specifying only the hyperparameters of the 2D convolutional layer, you can define this kind of layer, convolutional layer. Okay. And at the same time, when defining this, all the parameter sector is randomly initialized. Okay. And the next thing is for implementing the forward rule, you don't have to explicitly, write down the exact formula. Okay, so you seeing this formula, you by yourself type this kind of formula in your code, but because you by defining as the linear layer, the program already know that this net architecture is their forward formula. They already know about that, so you can now just call net and their input variable x. Okay, so when doing that in this form, when your forward rule is changed, you have to re-implement everything. But even though your forward rule is changed, if you code it like this code is not changed. Okay. So in PyTorch, this type of code is preferable. Okay. Okay, and also next, previously, this is a few more changes you have to have. So here, you already remember that the W and B, those are initialized by yourself. Okay, so for each variable, you have to initialize their gradient value as known. Okay, unless this gradient value have some garbage value inside. If you do not explicitly assign this known value, and also the thing is, actually, the gradient values are added to this initial value when you call this load step backward. I already told you that when you call load step backward, DLD sector for all the parameters are calculated, and they are calculated via the chain rule, and then they are actually added to initial gradient values. Okay, they are not assigned, but they are appended to the initial value. So that's why actually you are initializing each gradient value as known. Without this code, your gradient might be confused because that is actually added to some garbage values. Okay, so that's why we are initializing these gradient values. But if you have if you have many parameters within your architecture, initializing, typing this line of code will be hundreds of lines. So the PyTorch make it easy by providing you this zero_grad function. So you have to explicitly define this optimizer, which have access to all the parameters of this net architecture you already defined. So I already told you this net variable is having your architecture. Okay, this is doing the same thing as this, right? So and also this net dot parameters, it is returning these parameters, which are actually W and B in our case. The parameters that should be updated is returned when you call this net dot parameters, okay? And actually this optimizer is managing this kind of optimization part, okay? Okay, so optimizer should know all the parameter list. Okay, so that's why it is inputting these parameters. Okay, okay. So you first have to know which parameter you will update. So that's why it is having argument as this. Okay, and the other thing you have to know is this epsilon, the learning rate. LR is the abbreviation for the learning rate, and you already define this in here, initialize this as the small scalar value. And if you already know sector, their list, and this gamma, then the thing you need to know further would be this gradient, and that would be coming from this low step backward, okay? And after defining this optimizer, the thing you have to do is initializing all the parameter, their gradient as 0. So that's actually the code, what is happening here. And then you define the forward rule, okay? And if you call this low step backward, all the variables connected to the final loss within the graph structure are calculated with their corresponding gradient values, okay? You can calculate actually the DL dissector by calling this backward function. And then what optimizer does this function does is this part, okay? You can replace this as the optimizer does tab. So after calling low start backward, you already get DL dissector for all the parameters. Then for this formula, for the only thing you didn't know was this part, okay? You already know this from this parameter list and know this by initializing it with the learning rate, but you didn't know this DL dissector, but after calling this low step backward, you become to know about that. And the thing remained is just calculating this formula, okay? And that is actually happening with calling this optimizer.step function, okay? And this is appending the loss for visualization purpose, okay? So the same code here could be replaced with this line of code, okay? And another thing remained is, for calculating the loss function, of course, this Euclidean distance between the ground truth and prediction that is frequently used, but there are a lot of other loss functions that can calculate the distance between prediction and ground truth, okay? So when implementing deep learning training, we frequently replace this with other function, okay? So for reducing also the effort, changing this part, we can explicitly define the loss function here outside the iteration, and we can just input the predicted value and their ground truth value, okay? Actually, this loss function is the function that can find distance between predicted and ground truth y values. That's actually loss. There could be a lot of different loss functions other than the Euclidean loss, and you can just change these functions. Okay, and then you can, afterwards you don't have to change this part. Okay, every loss function is anyways, their method could be different, but they are calculating the distance between these two arguments, which is prediction and ground truth, using different methods. So you don't have to change this part, but instead you can just change this to change the loss function. Okay. And yeah, then this is the code actually. This is actually the training code that can be usable for any kind of differentiable layers. Okay, so especially this part, maybe later you will see, and these parts are not changed regardless of the loss function or which optimizer you will use and which architecture you will use. Okay, so the first step is just initializing gradient for all the parameters within the deep architecture, and then you apply forward step to calculate the loss from the initial input variable, and then calculate the LD sector for all the parameter and update the parameter sector using this direction. So it is done for all the iterations. So this 5-step algorithm is not changed, but you can just change which loss function you will use and which optimizer you will use or your network architecture later. Okay, these three things are changed, but this algorithm, the gradient descent algorithm, is not well changed. Okay, so you will see this proceed. The algorithm is used for training any other architectures. Okay. So this is the pseudocode for training. So data preparation, we have to define the ground truth and x and y, randomly initialize the parameters. And here we have to define our network structure, optimizer, and loss, and then iterate through this gradient descent with these 5 steps. Okay. And actually, this is the fix. And the thing you have to change is the 3 line of information. Okay. Okay. So, and I will briefly also introduce this multi-layer perceptron. As I mentioned, this linear regression is the simplest form of the regressor. Okay. But if you stack few more linear regressor with activation layers, then that becomes the multi-layer perceptron. So, their formula looks like this, but these individual layers are linear layer, okay? But here, there are activation functions we have already learned. This is either ReLU or tangent hyperbole or let's say the sigmoid. Okay, they are actually the sum of the nonlinear function applied after the linear layer, and then you apply another linear layer and apply another nonlinear layer and apply another linear layer and then apply another nonlinear layer. This is the multi-layer perceptron. So multi-layer come from because you have multiple layers, and perceptron is this kind of linear. They are pointing out this kind of the unit, okay, and this is inspired from our brain having the neurons inside. So this type of basic unit is thought as the neuron in our brain, and actually in our brain, these neurons are combined together to represent complex signals. And so it is this kind of formula that stack multiple linear layers I mean, the researchers think this similar to our brain. Okay, they are composed of the neurons, simple neurons, with some activation, this kind of nonlinear layers, okay, to represent complex signals. Okay, so actually MLP, we call this as the MLP, okay, multi-layer perceptron. This is inspired from our brain, and actually, I will show you why there should be some of the nonlinear layers in the middle of the linear layers. I mean, I will show you the case where nonlinear layers are not there. So if you stack multiple linear layers without involving this nonlinear layer, then you can simplify the formula like this, okay? And then you can see that complex architecture, their output becomes a simple linear layer, okay? So this is complex, but it's denoting only the sum of the linear coefficients, and the other part without x, that is complex to calculate, but it is converging to some constant. So if we do not use this kind of nonlinear layers in the middle of the linear layer, then the entire layer becomes complex to calculate, but it converges to a simple linear equation. Okay, so that's why we have to involve this kind of nonlinear layers in the middle of the linear layer, and it can actually give us some of the nonlinear characteristics that can map x to y. Okay, so this is the reason why we have to involve these nonlinear functions. Okay, and I will show you maybe in the next class how we can implement the training of these more complex MLP layers with the same PyTorch code. Okay, so this is the total code to train these MLP layers, and you can see that these 5 lines of code is same as before. I mean, same as the linear regression case. The thing you have to change is just the architecture now. So I already told you that this torch dot and then the linear, that is, denoting the simple linear equation like this, okay? We now have multiple linear layers inside. This torch dot and then the sequential means you will stack these layers one by one. Okay, you will apply these layers one by one to your input and intermediate inputs to calculate the final output. So you first apply this linear equation, and then apply nonlinear, and apply linear again, and apply nonlinear, and linear, nonlinear, linear. So this becomes the architecture that represents this kind of formula, right? So the thing you have to change is actually this net architecture, and loss function, we will use the same mean square error loss, actually the Euclidean distance between prediction and ground truth. And also we will use the same optimizer, the stochastic gradient descent algorithm. Okay, I will explain this SGD later, but you now know gradient descent. Okay, so gradient descent and SGD, their formula is same, so we can use this function implemented in the PyTorch. Anyways, these two informations are same as the one we use when training the linear regression algorithm, but different thing is the architecture definition, okay? And this is the data generation part, okay? And using the same training code, 5 lines of same training code, you can train this MLP structure, okay? I will show you that, next Monday, okay? And also we will learn about how to train this CNN architecture using the PyTorch library as well. And then I will show you also some of the different loss functions that can train the classification architecture, and we will see some of the more complex CNN architectures. Okay. So for today, let's finish here. Thank you. See you next Monday.